Okay, so I'd like to introduce Professor Xavier, who's a distinguished professor of astronomy and astrophysics at the University of California. His research sheds light on the early cosmology and structure formation in the universe, including the formulation and evolution of galaxies. And in this session, now we hope that we'll learn more about him from the talk that he'll give. And over to you, Professor X.
Thank you, and good morning, everyone. At least good morning from this side of the world. It's great to visit South Africa without the 16-hour flight it would normally be or something like that, but I would like to do it someday. It's on my list. I've yet to be in that continent at all. And anyways, today I'm going to probably introduce most of you to fast radio bursts. Perhaps there's an expert or two in the audience, I'm not sure. Let me share my screen and give you a sense of why I'm excited about these phenomena and maybe inspire some of you to think a bit more about them. And here we go. I will pause along the way to let you ask questions. I've got, maybe 50 slides, but I don't have any intent to get through them all. So by all means, make this interactive and a good learning experience for you. I'm Xavier, or X. I am here in Santa Cruz. The sun's about to rise. Not quite yet. And I'm a member of the fast and fortunate for FRB follow-up team, as we call ourselves, F to the 4. And we collaborate with a number of teams across the world, including South Africa. That's the SmearTrap team, or they use the Meerkat telescope in South Africa. The team is distributed to study fast radio bursts. And that's the focus of today's presentation. A few words about the team, the F4 team, that is. Here's kind of the current core team, which has a diversity of academic age. I'm the older person in the team. We have a nice young crowd, also distributed a bit across the world. Nicholas is in Chile. We actually had a person in South Africa. She's now graduated. And as I said, we collaborate with folks across the world to do science with fast radio bursts. So I want to acknowledge this team. A fair bit of what you'll be seeing today relates to their works, their efforts. Let me begin with a kind of overview of what FRBs are, fast radio bursts, FRBs. And I've structured the introduction to use a little help from gravitational wave events, GWs, gravitational waves. Maybe you're a bit more familiar with those. If you're not familiar with gravitational waves, you're going to get a little introduction to each. So here we go. If you've been paying attention to one of the biggest advances in physics over the last few years, 5 years, 10 years, that's gravitational wave science, using wonderful new detectors to now detect the ripples in space-time that Einstein predicted are a manifestation of his general relativity theory. This is some artist's conception of those ripples in space-time, here being generated by two inspiraling compact objects, maybe black holes. Gravitational waves, they are detected in these tubes, evacuated tubes, where we shine lasers down about 1 kilometer in length. This is an interferometer. So one measures the space-time here on Earth and looks for ripples in that space-time with these large interferometer detectors. That's how physicists detect gravitational waves. That's the tool we use. There are 2 of them here in the United States, and now one in Italy and one coming in India. I think I have that right. For fast radio bursts, the tools can be a bit more archaic. This is a radio telescope in Australia. It's called the Parkes telescope. You can tell perhaps from the architecture, it's good old 1950s and even earlier. one requires a radio telescope and its associated detector to detect a fast radio burst. Although you'll see as the talk goes on, we also take advantage of interferometers for this science. The signal of a gravitational wave looks a bit like this. The x-axis is time. So here again, picture an in-spiraling set of, say, black holes. At the very end of that in-spiraling event, as the two coalesce, as they come together, they spin up more rapidly, hence the frequency, the y-axis increases, and one detects gravitational waves with increasing frequency at the very end of the in-spiraling event. Amusingly, the signal of an FRB is quite similar. The x-axis again is time, and the y-axis again is frequency, albeit it's gigahertz, not hertz. So 10 to the 9 times higher, or nearly that in frequency. And this sweep, so the signal is the black line that I'm tracing with my red dot. This sweep is what defines a fast radio burst. This delayed arrival time, that's what you're seeing here. The lower frequency radiation, so lower frequencies towards the bottom of the figure. The lower frequency radiation is arriving at later times than the higher frequency radiation. And that's due to the propagation of light, radio waves, through a plasma. Here, electrons. And there are electrons distributed throughout our universe. I'll speak more to this later. But as the light travels through a plasma, the speed of light is retarded, and the effect of that plasma is greater for lower frequency radiation. And so this is kind of electromagnetism 101, at least electromagnetism in a plasma. And it's what really defines a fast radio burst, this so-called sweep. And so people design software to detect sweeps like this, pulses of radiation at the radio telescope. Where do these signals come from? The gravitational waves, undoubtedly now, I'd say we have proof, come from coalescing compact objects, at least the ones we can detect. I suppose that everything, nearly every object with a mass can be creating gravitational waves and is probably creating gravitational waves. So the ones we detect are somewhat massive compact objects. Fast radio bursts, that's kind of an unknown. It's partly what makes the field exciting. We've got these chirps of bright radio emission coming from across the universe, and we're still struggling to make out what are the origins of these signals. A prevailing model or best bet are magnetars, highly magnetized compact objects, neutron stars, that are somehow chirping on occasion or perhaps repeatedly to make these FRBs. But that puzzle remains. What is some of the science we can do with these signals? Gravitational waves, a lot of the science is focused on compact objects. So the demographics of black holes, of neutron stars, fantastic new window into studying those phenomena. With FRBs, the signal is undoubtedly coming from something like a highly magnetized plasma. This is complex and challenging astrophysics related to, if you've thought about pulsars, studied pulsars, related to that astrophysics, also challenging, also kind of a decades-long problem to solve for how the pulsar mechanism works. Now we have the challenge of figuring out how these FRBs emit their radiation. What really excites me about FRBs, however, is to use them to probe the universe. And that's true for gravitational wave events as well. So with gravitational wave events, if you can pinpoint the location of that event and establish the galaxy that it's coming from, where these black holes exist, you can use that distance, that redshift, plus the signal itself to make a constraint on the expansion rate of the universe, what we call H0, or Hubble's constant. This is an inference of the Hubble parameter from one of the gravitational events in 2017. It's not a very constraining measurement today, but there's certainly great promise for doing that exceedingly well going forward. What brought me into the field of fast radio bursts was the potential to weigh the universe. And by that, I mean to measure the mass density of ordinary matter in our universe. And I'll have more to say about that in the slides to come. But not using the signals, not studying the signals to figure out what causes the FRBs, but leveraging the signals, taking advantage of the signals we detect to make an inference about our universe, the cosmology of our universe. Let me pause there. That was my introduction to FRBs. I presume most of you are not experts in this field. Let me open the floor if you'd like to ask a introductory level question. Anything is fine. Let me pause there. Hearing nothing, I'll continue. This field has gotten especially exciting from my perspective because of the rise in our detection of these FRBs, and I'm going to describe that now and go through a little bit of the history of the phenomena. It's a pretty young field in that it's actually a very young field by astronomical terms. The first event detected is this one. You've seen it in the previous slide. This is the signal again. And it was published in 2007 by Duncan Lorimer. But it was actually recorded in by the telescope, the Parkes telescope, in 2001. So still only about a 20-year-old phenomenon, quite young by astronomy terms. It took him 6 years to even discover it was there, and it was sort of by accident, which is kind of an amusing aspect. There's a number of kind of quirky things, peculiar things about fast radio bursts. This is one of them. It was a serendipitous discovery. Professor Lorimer was searching for pulsars in something called RRATs, pulsar-like phenomena, towards the Magellanic Clouds, which you all have a nice view of down there in South Africa. And he had modified his software, which he was using to detect pulsars, in a way that he shouldn't have. He opened up the parameter space to detect pulsars that just never exist in the Magellanic Clouds. And lo and behold, this thing fell out of the sky. It was a phenomenon he was totally unanticipating, and led to discovery of this first fast radio burst. And what was unusual about it was the degree of this sweep. So again, I mentioned the signal itself is the strong black line that's sweeping across the figure. The degree of this sweep, the slope, if you will, is set by how much plasma the light travels through. And here's the crux of the physics. The arrival time, tau, is proportional to the frequency of the inverse square. And that's why shorter frequency light arrives at later times. It's inversely proportional to the frequency squared. And then there's this other term, dm. It's what we call the dispersion measure, dm. I'm going to refer to it quite a bit from here on. So please see if you can understand it well. Dispersion measure is the path integral of the material, and really it's electrons, that the radiation travels through. So it's a path integral. S is the path. How many electrons lie between us and the source? For pulsars, we have pulsars throughout our galaxy. There's pulsars in the Magellanic Clouds. But for pulsars in the Milky Way, this integral is, from us to the pulsar in, say, one of the spiral arms nearby. And the more electrons between us and that spiral arm, the larger this dispersion measure and the greater the sweep in the signal. If you go to cosmological distances, so if you have a source that's far away, very far away, outside of our galaxy, then there's an additional 1 plus z term, z's redshift, what we call the scale factor. All right, so what this means is you can use, by measuring this sweep, which is really quite straightforward in the data, you directly have a measure of how much material lies between us and the FRB, okay, or us and the pulsar, if you use a pulsar. And the point of the Lorimer discovery, this first fast radio burst, was that there was way too much material. The sweep was way too large. The dispersion measure was way too large for the source to have originated in the Magellanic Clouds. There's just not enough material between us and the clouds, given what we know about our galaxy and those galaxies. So he inferred, and he was correct, although there was skepticism at first, he was correct in inferring this FRB must exist well beyond our galaxy in the Magellanic Clouds, outside in the distant universe. So he proposed, and he was correct, that this was an extragalactic source, hence extremely bright, so that we could see it here at Earth. Any questions on that? Any questions about the dispersion measure? This is really critical to the talk and the science that follows. Yes, sir, Eric.
Yes. So when you mentioned the sweep, right, the sweep being large, does that mean the gradient is steep, or
it's the larger the DM, the shallower the slope of this line. So if I had a very small dispersion measure, the sweep would be almost vertical.
Okay.
And the more I increase dispersion measure, and the way, from the physics, the more I increase DM, then the more I'm increasing tau, and that means the photons take longer. They get pushed to the right on the x-axis. Okay. Yeah. So a greater sweep, and this means a shallower slope. Good question. Anything else? Okay. And then this was just, as I said, this was published in 2007. It certainly caught my attention because as I will emphasize, I've been really struggling, and as were my colleagues, to measure gas in our universe. Most of the material out there is very diffuse, very difficult to detect, as it emits almost nothing. And so we were really struggling to measure the material out in our universe, in the intergalactic medium, as we call it. And this clearly presented a new opportunity to do that. And indeed, that's what we've been using them for of late. However, after the publication, for the next maybe 10 years, FRBs were kind of a novelty of the radio astronomy community. There was skepticism about whether this first event was extragalactic. There was a handful of additional ones detected. Some of them were linked then to microwave ovens. Crazy story I'm happy to talk about. They weren't actually, astrophysical, but spurious. But nevertheless, the field kind of bubbled along until this FRB was detected and analyzed and followed up. So it's called the repeater by the community. It's got this name. The name, the data was discovered. It's also now known as R1. I'll probably just call it the repeater. And we call it the repeater because not only do we detect, a signal from it once, but over and over again. So this source, this FRB, has been emitted multiple times. In fact, I don't know, probably hundreds now, since the first one was detected. That's neat. That tells us at least some of these phenomena aren't explosive or destructive. Supernovae, they go off, they make their signal, they go away. Some of these fast radio bursts are here to stay and repeat over and again. But what really made this useful to the field was that because it repeated, one could point to interferometer, in this case the VLA in North America, and pinpoint on the sky its location. And so that was what was done. That's what this figure shows. The box, I guess, shows the localization with the VLA, another radio telescope one with an interferometer, so that we could pinpoint it to even less than 1 arc second on the sky. And when one took a follow-up optical image, the blue here is an optical image of the sky at that position, zoomed in. There was a small smudge, a dwarf galaxy, if you will, now known to be the host of this repeating fast radio burst. And so sure enough, proof positive that these sources do occur in galaxies outside our own and are cosmological or extragalactic, and clearly now set the stage to use them as probes of the universe. So R1, or the repeater, really was a big breakthrough. That paper was published in 2017, so 10 years after the first one. There was kind of the first secure evidence, really secure evidence that they're extragalactic in nature and occurring at great distances. Over the last, say, 4 years, maybe 5 years now, there have been technical advances which have driven the field. Two telescopes in particular have come online to detect fast radio bursts. One is Chime, which is an experiment in Western Canada. It's got terrific sensitivity. It's detecting several fast radio bursts per day. I'm told they have 4,000 in hand, where in 2017, this previous slide, there were maybe 30 known. Now we have 4,000. So it's been an absolute explosion in data. The downside, if you will, of this experiment is that it doesn't localize the events to very high precision. There are arc minutes on the sky, and so you can't determine which galaxy in that region hosted the event. But they're fantastic. It's a fantastic survey for studying the population of FRBs and many other things, which I'd be happy to describe, but won't say too much more about in this talk. The other technical advance is using this telescope called ASKAP, the Australian SKA Pathfinder. It's the sister facility to what MeerKAT is in South Africa. They're both pathfinders for the SKA. This one's in Australia, MeerKAT's in South Africa. Both are now detecting fast radio bursts, as I mentioned at the start of the talk. There's a team using MeerKAT. We're involved with them. I don't have any results to show from their efforts today. They're still ramping up, but do have nice results. ASKAP was up and running first. The team known as CRAFT, this one up here, has a system on the ASKAP telescope to detect fast radio bursts. Because it's an interferometer, ASKAP, as is MeerKAT, when we detect a fast radio burst, not only do we detect it, but we localize it as precisely as even 1/10 of an arc second. And that's ideal for pinpointing what galaxy that the source exists in, and hence the distance to it via the redshift. The rate of detection is modest compared to, say, the Chime experiment, maybe about 10 FRBs per year. But they're just now completing an upgrade to the system that'll increase the detection rate by almost an order of magnitude. So we're expecting about 100 FRBs per year with the system, starting in this fall. Why, again, let me make clear why the localizations are so important. So when you do localize a fast radio burst to 1/10 of an arc second, say, or an arc second, you take an image of that region, and if it lands right on top of a galaxy, as the one I'm showing here, so here the black ellipse is the localization of the fast radio burst. The images are from the Hubble Space Telescope, pretty faint in the ultraviolet. Maybe ignore the left panel, but quite bright here in the near infrared. And that's a galaxy, kind of run-of-the-mill galaxy at, I think, a redshift of 0.4. We've developed a framework to associate FRBs to galaxies. We call it PATH. I'm happy to describe that in more detail if you wish, but I don't think you need much convincing that when you have this kind of association of the FRB to a galaxy, it's a secure association. And we have a very, very high probability that that galaxy generated or hosts the phenomenon, the compact object making the fast radio burst. With a big telescope like we have access to here in California, we can take a spectrum of the galaxy, characterize it, and learn about the galaxies that are generating these events. Today, nearly every radio telescope on the planet is searching for fast radio bursts. I've talked about Chime. Let's see, I mentioned the Chime experiment. One of these is one of these Meerkat? Does anyone know Meerkat? What it looks like? I think maybe this one is Meerkat. In South Africa. That's Parkes. This is the DSA in Owens Valley. That's the BLA. Anyways, and then there are, many other radio telescopes listed, some listed down below here, which are detecting FRBs as well. So the data collection rate has exploded to really hit home that point. Let me show you the known FRBs as a function of time. That's the blue curve. 2001 was the first one recorded in a telescope, published in 2007. As I said, there was a smattering in the 10 years to follow. 2017 was that first localized one, which is where the red curve is counting localized events. It turned on, well, the event was in 2012, but published in 2017. This is the Chime experiment turning on. Woo! That's an exponential rise. And this tail is only because they haven't published those 4,000. You should imagine the blue curve just continuing to rise off your screens. And then the red curve is driven largely by ASKAP and now Meerkat. And that also has been an exponential rise over the last few years. So the field is really exploding in terms of data. Let me pause there and ask for questions again.
So there are a couple of questions in the chat.
Please.
The first one by Lerato is that, is there similarity or distinguishing factor between FRBs and pulsar profile?
The main difference is that dispersion measure. Well, there's a couple of differences, but a key distinguishing feature is just that dispersion measure. Let me go back to that. As I said, Lorimer Duncan was searching for pulsars towards the Magellanic Clouds. There are, we believe, pulsars detectable from the Magellanic Clouds. Some have been detected. And we know how much gas there is in the Milky Way in that direction. We know we have some estimate for how much gas is in our halo, which I'll refer to in a minute. So the extended dark matter and gas around our galaxy, we call that the halo. And then we have an estimate for how much gas there is in the Magellanic Clouds. We can measure it with radio telescopes as well. And they're just, in this signal, there are far too many electrons detected to be associated with just our galaxy. And so that's the distinguishing factor. We measure pulsars throughout the Milky Way. They do show a range of dispersion measures, and some are very high. If a pulsar lies in an H2 region, a star-forming region with a lot of ionized gas, and there are a lot of electrons, you can have a very high dispersion measure. So there are distinguishing features. Most pulsars are in the disk of our galaxy. Not all, but many. And so they're distributed spatially in our disk, whereas fast radio bursts, I don't have a plot in this slide deck, but fast radio bursts are seen all across the sky. Great question.
And, can we safely say that also the fast radio bursts have a periodic signal like pulsars?
So this event, the first one known to repeat, aka R1, its cadence, if you will, is stochastic. It's not regular. There have been hints of some periodicity, but not really for this event. There are a couple, I'm not sure if it's 1, 2, 3, maybe 5, where there is quasi-periodic behavior. So I know of one which has roughly a 16-day cadence, which is a funny number, 16 days. And pulsars are milliseconds or seconds. Why 16 days, we don't know. But most have not been shown to repeat, although they might. It's possible, conceivable that they all will, but only a handful, only a small fraction have been shown to repeat. And of those that do repeat, most are irregular.
There's another question by Benjamin Hugo. Is there any evidence of these variable transients in X-ray?
Great question. So if we're going to unlock this mystery of what creates FRBs, a promising path, although challenging. I've worked on this. We've worked on this, is to look for the signatures of the event at other frequencies. X-rays is a good example. In our own Milky Way, one of the we have known magnetars. We have known neutron stars with extreme magnetic fields. We call them magnetars. Some of them emit X-rays on occasion. And one of those magnetars has also emitted a pulse of radio emission that looks quite a bit like a fast radio burst, albeit much lower energy, much lower luminosity. So there's reason within this magnetar scenario, there's reason to predict that not only should you see radio emission, fast radio bursts, but perhaps corresponding X-ray emission. People have been trying, we've been trying with X-ray telescopes, no success to date. So great question. It's something the community is pursuing. But as far as events outside of the Milky Way, there's not been a detection to date.
There's this other question also by Lerato. FRB is difficult to find like pulsars. I'm not sure if they are indeed difficult to observe, but there seem to be a few non-pulsars. Or the detection rate for FRB, is it more than that of pulsars?
It is now, and I guess that's because we have the whole universe to play with, more than any other reason. As far as the software involved so for both, I imagine, I don't know much about pulsars, let me admit that first, but I suspect the software that one uses, by and large, to search for a pulsar should be quite similar to, or if not even almost identical to what one uses for a fast radio burst. The signal is a sweep in this time frequency plane. What I didn't say, I'll say it now, which is pretty neat. For these facilities, for most of these facilities, not all, the software is running in the background. So people are using the Parkes telescope, this one, or the ASKAP telescope, or the VLA, to do some kind of radio science. And the data's flowing in, and folks like Kraft, there's a team that's then analyzing the data stream in real time for an FRB. You would think you could do the same thing for pulsars, and maybe they are, and I don't know, but I don't think they do, and I don't know the distinction why. But anyways, for fast radio bursts, these searches are going on commensally all the time, and that also increases the detection rate. We're searching, effectively every moment the telescope is being used, or at least we try to.
And the other question that I had was that, so is it possible to use the fast radio bursts to know, let's say something like the matter density distribution along the direction of the pulsar, or maybe also any other information, maybe like the spin temperature or such?
Oh, good questions. I'm gonna so I will spend another 10 slides, and you can then tell me maybe we're done on the first part of your question, studying the matter. So let's hold that for a minute. I'll even talk a little bit to the other signals. You don't get a spin temperature, but you can get from the polarization rotation measure, and that's sensitive to the magnetic fields that the signal propagates through. I could say I have some slides in here. I could show one briefly before we conclude. But let me focus on what you started to ask there, which was about the matter in the universe, or matter distribution. That's what really brought me into this field. And it relies on the dispersion measure, which I've introduced. Here it is again. It's the path integral of the electron density from us to the source. And what we need to appreciate is that there are a lot of regions, or a lot of portions of the universe between us and the source that can contribute. So I'm trying to cartoon that out, and there's quite a bit here. So here we are at the sun, or whatever, in the solar system, and on the other end over here is the fast radio burst, our source. we know the Milky Way, that's the green here, the interstellar medium, ISM, of our Milky Way has electrons in it. And we've detected those and even mapped those out quite well with pulsars. So those contribute to this dispersion measure, just like they do for pulsars. Our galaxy, and we believe all galaxies, have a halo. For our galaxy, maybe extending out to a couple hundred kiloparsecs. So 10-ish times larger than the disk of our galaxies. This halo contains dark matter, it contains normal matter, baryons, which means electrons as well, and those contribute. And we don't know how much matter is out there. In fact, that's one of the goals of using fast radio bursts is to infer that. And that's ongoing work. The Milky Way has its neighbor Andromeda, M31. We call that the local group. It's got a plasma in it as well, so it'll contribute electrons. That's out to scales about a megaparsec. So these are kind of local things. Local to us are the green and the blue. Our galaxy, its halo, and the local group that we live in. Then there's what I would call the intergalactic medium or the cosmic web. Let's use cosmic web. So the universe writ large, it has its material. It contributes to the electrons we detect in the FRB signal. And then close by the FRB itself is, I've shown you one example of an FRB in a galaxy. They all occur in galaxies to the extent that we've been able to measure. And its galaxy will also have electrons, its own interstellar medium, its own halo as well, that will contribute to the signal. So electrons here and here and here, all along the way, are part of this path integral and add up into the dispersion measure that we record. So I like to call FRBs kind of a blessing and a curse, or a blessing because we can study this diffuse matter throughout the universe. We're sensitive to it. They're a curse because we're sensitive to everything. And if I'm really interested in, and the next few slides I will be in the cosmic web, well, I have to understand how the galaxy that has a fast radio burst and our own galaxy, how they're also contributing to the signal. That's a bit of the curse of the FRB. But we have ways to attack that problem. So let me focus on the cosmic web for the next, handful of slides. What motivated the science, what motivated my research here was the fact that, or was something that we called the missing baryons problem. You may have heard of it, missing baryons problem. I will summarize it here in the next two slides. The missing baryons problem is this. As long as now 25 years ago, we had first good estimates of the cosmic baryon density in the universe. So it's this quantity, omega b. If you've taken a cosmology class, you've seen it, hopefully. But omega b is the mass density in baryons, normal matter, cosmic baryons. And we have two techniques now to measure that quantity from the early universe. Two techniques. One is using the cosmic microwave background, CMB. And the gray ellipses are estimates of omega baryon from the microwave radiation field. Okay. That's early, that radiation field, of course, comes from the early universe. And the other technique is using measurements of deuterium. D here is deuterium, H hydrogen. And so the ratio of deuterium, which is an isotope of hydrogen, to normal hydrogen, also sets an estimate on the mass density of the universe. And it's proportional to how many neutrino species there are. That's what N effective is. But we know that N effective should be around 3. There's about 3 neutrino species. So 2 experiments using this, one using the CMB, microwave radiation, and one using deuterium and theory from Big Bang nucleosynthesis, the formation of the light elements. 2 different techniques, both from the early universe, give exactly the same answer, or 2 of them uncertainties. The blue is the deuterium inference, the gray is the CMB, and the pink and red are the combined constraints. And this is about as powerful. I don't know how many cosmologists are listening, but if you're not a cosmologist and you've had some doubts about cosmology, which we all should be somewhat skeptical, this is about as strong an evidence of the Big Bang model as you can get. Two wildly different experiments, microwave background radiation, counting deuterium and hydrogen atoms, and Big Bang nucleosynthesis. Very different physics, very different data, very different experimental apparatus, give exactly the same answer, at least to within errors, to high precision. This, for me, is the most impressive cosmological measurement that I've seen in my career. Well, but anyways, the upshot is we know this quantity, the mass, we've estimated this quantity, that's mass density of the universe in baryons to high precision. Okay, great. So what happened next? Well, this was first being reported, these measurements were first being done, as I said, about 25 years ago. And these scientists, Fukugita, Hogan, Peebles, they took that number and they said, all right, well, if there's that much matter in the universe, we should be able to go out in our backyard today, redshift 0, and count up the baryons, see that they're there. So they did that. They went and they counted up how many baryons were in stars. That's the orange and the cyan wedges. How many baryons are in atomic gas? You can use 21 centimeter for that. How many baryons are in molecular gas? You can use carbon monoxide as a tracer. How many baryons are in X-ray clusters, X-ray emitting clusters of galaxies, that's the black. And so they added up these detectable sources of baryons, galaxies primarily, and to some extent intergalactic medium, and came up woefully short of the total. So the pie here is the total amount expected, and the yellow is was undetected. They proposed it would be in what they call group gas. It's probably not quite right. But this beget the missing baryon problem. Roughly half the baryons that we expect to be out there are undetectable. And we're talking about our backyard. We're not talking about trying to detect them, across the universe. We're just trying to measure them right around us, effectively. Yet we can't see half of them, and that was crazy, and a little disturbing. Although, astronomy is hard, so okay, problems like this arise. The theorists then, motivated by Fukugita's paper, said, well, we can look in the computers and we can tell you where the baryons are. And they propose it's in this warm, hot, highly ionized phase. It's got a name to it now called the WIM. Here's a phase diagram of their computer model. This is just a model. Density on the x-axis, temperature. And this WIM is low density. I'll remind you that dense gas in our galaxies is up here, 10 to the -1 or even higher. So very diffuse, quite hot, 1,000,000 degrees, 10 million degrees temperature, and very hard to detect. So they proposed most of the matter today around us is in this WIM, this diffuse, pretty warm, pretty hot medium. And myself and my colleagues, we spent decades using telescopes to try and detect it, and by and large failed. It's just too diffuse, we believe, or expect now, given our lack of detection, or just a bit too warm and hot. Enter fast radio bursts and those dispersion measures. They're absolutely the critical piece here. We need to know the distance to the fast radio burst, and we need to know its dispersion measure. And we now have access to both. How does dispersion measure play a role? Here's an equation, pretty straightforward cosmology calculation. It's the dispersion measure is the integral of the material between us and the source. Now putting that in cosmological terms, Z, what was ds is now dz, redshift. And here's the electrons. There's additional terms for cosmology. They're not too important to discussion here, but be aware they're part of the calculation. And then on the amount of electrons out there in the universe depends on the density of matter in the universe, and hence this omega b. I didn't define omega b previously, but here it is. Omega b is related to the mass density of baryons in the universe. That's what rho b is. And it's just time the critical density, which is some constants, including the Hubble constant. Okay, so if you have a prediction, a straightforward prediction from cosmology on what the dispersion measure of our universe should be, given how many baryons we expect that are out there. I should have said, here's some, again, computer simulation of the cosmic web. This is what we model the universe to look like. It's got this filamentary structure. That's why we call it the web, or a web, cosmic web. Galaxies are the little yellow dots. Groups and clusters of galaxies are the really big orange blobs or yellow blobs. And then there's diffuse matter throughout the universe as well. And this is the average dispersion measure from all that material in our universe. Here it is as a plot. So just plotting that equation or evaluating that equation as a function of redshift. X-axis is redshift. The farther you go, the more material you'll travel through, the higher the dispersion measure, dm cosmic. That's this integral that you would infer. And if you change how much matter is in the universe by, say, 20%, if you increase the amount of matter in the universe, then you would increase the dispersion measure and what number of electrons you would travel through. It's also sensitive to H0. I'm not going to get to that discussion today, but that's one of the things we're using these data for now, is to constrain the expansion rate. Okay, so if the baryons are out there, as we undoubtedly expect they are, then this is the prediction for the dispersion measures we should record in these fast radio bursts as a function of their redshift, as a function of how far away they are. So we have a clean prediction from cosmology for how these two quantities relate, and it's simply this interval. Okay. Let's do that experiment. We desire this to measure how many baryons are in the universe. We measure this in the data. Okay, and as I've said before, what we observe is the contribution of everything between us and the event. So our galaxy, that's these two terms on the left, the Milky Way, and the galaxy of the host, that hosts the FRB, that contributes to. We have a very good estimate for this, how much material is in the interstellar medium, so we can subtract that off just fine. We are less certain about these two quantities, so we model them in what follows. We have estimates, but they're uncertain. And we use a log normal PDF for that, if you're interested in the details. And then we can invert. So we measure, again, we measure the blue, we subtract off. So we measure the blue, that's this term. We subtract off the interstellar medium, which we know well, and some estimate for the halo of our galaxy plus the host of the FRB. When we do that and we apply it to the first sample of FRBs that we detected with good secure localizations and redshifts, this is what we recovered. The black curve, again, is the prediction from our cosmology using the early universe measurements for the mass density. The colored squares are fast radio burst data. And those with high quality measurements and passing other selection criteria. And the gray band is a prediction for the scatter around the black line. So this is the average. The black curve is the average dispersion measure we expect. The gray band shows a prediction for the scatter, the physical scatter. It's not an error, but there's an actual sightline to sightline scatter. And you can see that also well describes the data. We published this, I guess, 2 years ago now as a proof positive that, yeah, the local universe does have all the baryons out there. They were very difficult to detect by other means, but using these fast radio bursts, using their dispersion measures, we've now determined that indeed the baryons are not missing. They're there, and we've detected them. And this was a formulation of that measurement. I'll take questions on that in a minute. Maybe I'll take questions on that now, and then I could just say I have a few slides on where the future of FRBs are. So let me pause there. This is kind of a punchline slide of the science with FRBs.
Hello?
Yep.
Hello. Yes. Hi. Very nice talk. I wonder how much systematic there is for removing the term of DM host and DM Milky Way and the other component other than the IgM. Yeah.
That's right. So I think the question was, I missed the very start of the question, but you were referring to the 2 question marks, which are
yes, exactly.
Yeah. So to do the analysis, we adopted a model, parameterized model for the host and the halo, and allowed those to be free parameters for their contribution, and then integrated over we marginalized over those nuisance parameters to make this inference on the total mass density of the universe. So it's part of the model. It's a forward model. The shape that we use, this log normal PDF, it's motivated by the data and by our expectation for galaxies, but it's probably not the exact. No, I'm sure it's not the exactly correct functional form. But thus far, it seems like a pretty good description. So we've accounted for it in the analysis. It does lead to the some of the uncertainty that you see in this distribution in this PDF.
Okay, so there's also another question here by Lerato.
Yes.
So the baryons are not missing, but in the form of the warm ionized medium. Does this mean that the dark matter is no longer in the picture?
That what? Say that last part.
So the baryons are not missing, but in the form of WIM. Yep. Does this mean the dark matter is no longer in the picture?
So dark matter, we're not, with fast radio bursts, we're not sensitive to dark matter. Let me answer it this way. So, okay. This is, again, a computer-generated description of the universe, of the cosmic web. And what drives most of the structure here is dark matter. So the filaments that you see, the clusters that form, that's gravitational collapse. Dark matter, we estimate dominates the matter in the universe, and so it plays a leading role in the structure that forms here. The average DM doesn't, well, there is a term, dark matter contributes to this term, so dark matter plays a role here too, but it's, say, not a leading role. Where dark matter really can play a role and does play a role in this analysis is in this structure that we see, right? In the structure of the cosmic web. And I referred to it rather quickly in this plot. I'm going to jump between these 2 slides. Again, this gray band, so the black is the mean. It's pretty ignorant of dark matter. But the gray band is a function of structure in the universe. It's also a function of how galaxies form. So there's multiple processes that matter here. But let me explain how dark matter is relevant to the gray band. Back to this figure. If I have a sightline to an FRB that goes through the universe and misses most of the structure, so I'm trying to do that with my red dot. I'm avoiding most of the galaxies and kind of going through the most diffuse space universe. Then I'll get a dispersion measure that's lower than the average. If instead I go through the universe and I hit a lot of structure, then I'll be above the average. And so that's what that gray band is. It's sensitive to how much structure the individual sightline intersects. And so dark matter, how much dark matter in the universe does play a role in the shape of the cosmic web, and hence the scatter around the mean. So it can play a role there. As I sort of also mentioned, so too does galaxy formation. So there's kind of both competing effects or complementary effects in that scatter. But otherwise, dark matter is not playing a real role in the dispersion measure.
So, like, personally, if I've understood correctly, can you say that since dark matter in itself can't interact with radiation, it plays a role by creating matter, and the matter is the one that actually plays a role in the dispersion measure?
It plays a role by the distribution of the matter, and the more clumpy the universe is, the bigger the scatter in this relation. So the bigger the gray band is, the more clumpy the universe would be, then the bigger the scatter about the mean. And the more smooth the universe would be, the smaller the scatter about the mean. That's the way you should visualize it.
And the source of the scatter will be just ordinary matter, not dark matter in itself that's scattering.
Well, it'd be scattering the ordinary matter, but that would be driven by the dark matter distribution. So that they go together. On large scales, at least the way we, our understanding of the universe, normal matter traces dark matter. They go together. So the more structure that you have generated by dark matter, the more clumpiness, then the bigger the scatter in this relation. Physical scatter in this relation. As we're hitting the hour, let me just give you a few slides. I'm going to jump through the Hubble. If you're interested in Hubble's constant, if you're some real cosmologists, I could send you some slides on that. Or they were just recorded, you could look at them. And I'm going to skip over, you had asked about the signal. Here's, rotation measures, another part of the signals in fast radio bursts. And that gives you sensitivity to the magnetic fields. So there's ways to study magnetic fields in galaxies. I'm going to skip through that. I just want to show a few slides on where FRBs are headed, in case you are a little bit excited and want to know where the field's progressing, at least in my view. One now is, we detected we detected the missing matter, missing baryons. Now we want to know where they're located. We have predictions of this WIM, but we're doing experiments mapping out the cosmic web with fast radio bursts and galaxy observations to actually test this structure of the cosmic web that I've been showing you from computer simulations. So that's an exciting aspect of the experiment. That's another related thing. I've mentioned that the Milky Way has a halo of gas. This is a prediction for the dispersion measure map of the Milky Way and its halo and the Magellanic Clouds, which again, you all get a nice view of down there. Using fast radio bursts, we can map out this material of our own galaxy and its neighbors. Andromeda is over here. I think that'll be happening in the next few years. And that was the detail on that. As I said, it's basically a data overload, thousands of events. We're going to have hundreds of well-localized FRBs in the next year or two. Okay, and that's my summary slide. I can take more questions.
There's another question in the chat. You may have mentioned this already. Are FRBs used to constrain cosmological parameters, short FRBs or fast FRBs? Does it even matter?
I like those questions. So the short, let's see, referring to the pulse duration, there's actually not been a lot of work yet on the pulses. It's expensive analysis. There's probably order 10 published, but there are many detected. So that area will grow. Look forward to it. As far as the question about cosmological parameter, yes. Let's see, I'll show you. This is a punchline. This is a prediction. This is not real data of what constraint one could derive with 100 FRBs, well measured. And so this is a full with half max of about I think 6 kilometers per second. So it's not a very precise measurement, but it's a pretty precise measurement, and one that would be useful to resolving, hopefully, some of the tension on H naught. And maybe I'll just show you that slide. There's backup slide or related slides that here that I didn't show, but yes, we can use FRBs to constrain a Hubble parameter in the future. Today, I can show you. This is our current measurement, which looks good, but note the x-axis. It's many tens of kilometers per second, so this is not a precise measurement using only 16 FRBs. But with 100, you might approach something like this, which would be pretty exciting.
There's also this other question. So it seems the DM is direction dependent. Will it be possible or even practical to integrate the DM over all directions? What would one expect if this were possible?
So I heard the DM is redshift dependent. That's correct. The cosmic term is redshift dependent.
Oh,
and
no, I mean direction dependent.
Direction dependent. Yes. So the primary, go back to this slide. And I'm not showing the interstellar medium. So yes, you expect a directional dependence for FRBs, but it should be almost entirely dominated, or maybe it should be entirely dominated by the Milky Way. That is, once you get to extragalactic scales, we expect isotropic behavior. That is no directional dependence. But the Milky Way has an interstellar medium, which is not shown here. I may have a figure of it. No, I don't have it in the slide deck, sorry. But the Milky Way has an interstellar medium. I think it's oriented along the x-axis, yeah, in this figure. And that's a big signal, not shown. And then the halo may have some anisotropy, we don't know. And then galaxies, nearby galaxies to us, will impose directional dependent contributions to the dispersion measure. And we're going to invert the problem. We're going to measure that, that directional dependence and use it to make constraints on how many baryons are in Andromeda, hopefully how many baryons are in the Magellanic Clouds, those types of things. But beyond the Milky Way, beyond the local group, we anticipate there be a very minimal directional dependence.
Okay. There seem to be no more questions. But thank you so much for.
I have a hello. Am I audible?
Yes.
Hello. Yes, am I audible?
Yes. Yes.
Oh, okay, great. Yeah. I raised my hand in the participant list, so maybe you haven't seen. Okay. Anyway, it's a great talk, Professor Prochaska, and I mean, I'm a cosmologist, and I wrote a number of papers on this topic before as well. And I wonder, because in terms of cosmology and astrophysics, eventually for FRB, you can only constrain like a DM. So, I mean, these parameters are mostly kind of degenerated. And so in the future, how do you view the capacity of using FRB to constrain cosmology versus constrain astrophysics like baryons and so on? Yeah.
Gotcha. Let me speak to, I'll stick with H naught, which I think is, as far as cosmology goes, probably the most tractable quantity one can constrain. And I'm going to go into a little bit of the detail of how that's done. You may be familiar with it, but this will be maybe for the rest of the audience. So this is a prediction. Is that the slide I want? Yeah, let's use this one. Similar. Okay, so what's being plotted here, the axes first are redshift and dispersion measure. And now it's the extragalactic dispersion measure. So it's the one we measure, DMFRB, minus the Milky Way. But the host is still included. So it's cosmic plus host if you've been following along. But this quantity I think we can measure pretty well. Right? The host is another can of worms, which I think is part of the question here. And the color scale is a prediction, it's a model, for the probability of where FRBs should land in this 2-parameter space. So these are two, I call these two observables. Redshift is an observable, DM extragalactic is effectively unobservable. And so the color shows, again, a model for the prediction of the probability distribution of FRBs. This is for the ASKAP telescope. You would get a different prediction for a different telescope. And to make this model, it's quite involved. You have to make assumptions or a model of the host contribution. You have to make a model. The model has to include FRB energetics, their luminosity function, spectral energy distribution, things like that. Some modeling of the signal itself, its width, which we touched on briefly. The telescope plays a role here. And then in this model, we've also varied the Hubble parameter. Okay. So where cosmology can, where we can, because my optimism for saying we can place a constraint in cosmology comes from the sharpness of this PDF. So, you can, the dotted line, the dash dot, the dash, those are contours of the PDF, the probability distribution. I think 68%, 90%, 99, I think are contours. And you can see it's very sharp on this end. And that's where the constraining power for H naught comes. And these curves are the same or similar to this dash dot curve here, showing the 90th percentile contour of where we predict FRBs would lie in this space. And what I'm doing is I'm varying H naught, red, black, blue, and increasing it. And as we increase H naught, these contours tilt downward, which is a bit counterintuitive. I can go into detail if you want, but maybe just accept it for now. And that's where the constraining power is on H naught. And it's orthogonal to some of the effects well, the main effect that I would worry about would be the host dispersion measure, which is purely vertical in this plot. And so the bottom line is the behavior of how FRB should lie in this plane as a function of H naught runs counter to the way they are predicted to lie as a function of changing other parameters in that model. I'll allow, you could introduce degeneracies by having pretty unusual prescriptions for the host DM. And those are things I think we'll be able to test going forward. But today, the data would allow such a degeneracy.
Okay, am I audible? Hello?
Yeah.
Okay, great answer, yeah. And by the way, Professor Prochaska, I saw your name on the FRB IAU meeting list. Are you going?
I am, or at least I plan to, yes.
Okay, I'm also invited to go there. My name is Yin Jae Ma is on that list. So I'm very looking forward to see you in Busan, South Korea in August.
Hope, yeah, me too. Please, let's chat there in Korea.
Okay, great. Yeah. Nice to listen to your talk. Thank you. Yeah.
Thank you.
Thank you so much, Professor X, for the presentation.
My pleasure.
We do appreciate it.
Thanks for all the questions. It was really an enjoyable morning.
Right. Okay, so I believe we'll end the session here.
Enjoy the rest of your days.